Hi, hello friends, welcome to my YouTube channel. Now in this session, we would like to discuss the Aptransco 2000 AE electrical solutions, and the subject is control systems, and the weightage of the subject is around 8 to 10 marks for AE. Okay, next one. The first question here is introduction of integral action in a forward path of a unity feedback system results in. So when we are introducing integral action, so integral action means we can give the transfer function of integral action g is equal to some constant gain into I divided by s here. So here one thing you should be remember, g is proportional to 1 by s. So by introducing integral action in the forward path of a unity feedback system, what we are doing here is we are increasing the type of the system. As the type of the system increases, the steady state error is going to be decreases. So as you are increasing the integral action here and feedback system, so automatically the error is going to be 0. So the answer here is it's a B. Next question. The next question is the closed loop transfer function of a closed loop system is given by, so C of s by R of s is equal to 1 by 1 plus s. For the ramp for the input R of t is equal to sine t, the steady value of C of t is given by, so here we are having a transfer function which is given by 1 by 1 plus s, and the input to this transfer function is sine t, and we need to find what is the output here. So whenever we are giving sinusoidal input to transfer function, uh, the output will change its magnitude as well as phase angle. Okay, this is what we can call a sinusoidal steady state analysis. Now by comparing the standard equation, sine omega t, so sine omega t here, by comparing what we can say omega as 1. So this is very important. Once you identified omega is equal to 1, and the later part is very easy. So first we need to find magnitude. So magnitude is equal to 1 by, okay, so square root of 1 square plus, so instead of s I can take omega, so omega square. Why? Because s is equal to j omega, we substitute in sinusoidal steady state analysis. So as omega is equal to 1, so omega is equal to 1, then m is nothing but 1 by square root of 1 square plus 1 square. It is equal to how much? It is 1 by square root of 2. So we found the magnitude. Now phi I want, so phi is nothing but, so minus tan inversion of omega by 1. So if we substitute omega equal to 1, minus tan inversion of 1 is nothing but minus 45 degrees. Now the overall output C of t, so C of t is equal to, now we got magnitude is 1 by square root 2 into sine omega is 1, so t, and the phase difference is how much here? 45 degrees, is nothing but pi by 4. So pi is nothing but 180 degrees. So pi by 4 means we got 45 degrees. So the answer here is, it is D. The next question is the impulse response of a initially relaxed system, linear system, is e power minus 2t into u of t. To produce a response of t into e power minus 2t u of t, the input must be equal to. So here friends, the first thing is we are here having initially relaxed system, so linear system, so linear time invariant system is here, and the output what we are getting here is e power minus 2t into u of t we got here. Now what we are doing, what here is, suppose if you want to produce the output t into e power minus 2t into u of t, what will be the change in input? So what is the input you want here? That's it. So we'll take the we'll get the solution with the help of formula here. So the input must be given is equal to L inversion of Laplace transformation of output, that is t into e power minus 2t is the response output. What is the input? Laplace input means e power minus 2t here. So this is a formula that we are using here. So I forgot here. So u of t here and u of t here. The formula that we are going to use here is So t power n into e power minus at, if you have a Laplace transformation of this function, you will get it as n factorial divided by s plus a n plus 1 is a formula here. Okay, now based on this formula, we will get L inversion of Laplace transformation of t into e power minus t. So 1 divided by s plus 2 whole square divided by 1 by s plus 2. So L inversion of 1 by s plus 2 we got finally. It is nothing but e power minus 2t into u of t. So the answer here is C is the right answer for this question. Next question. The next question is the characteristic equation of a feedback control system is 2s power 4 plus s cube plus 3s square plus 5s plus 10 is equal to 0. The number of roots in the right half of s plane. So the number of roots in the right right half of s plane is nothing but number of sign changes in RH tabulation. So RH table. So we will form the RH tabulation here. So first one is, let me take different color. So s power 4 s cube right here. So s power 4 s cube s square s power 1 and s power 0 here. The first one is 2 and second one is 3 and 10 1 5. When you cross multiply here, so 1 into 3 minus 10, it will leads to minus 7, and here it is 10. 1 into, if you take 0 here, 1 into 10, 10 minus 2 into 0 divided by 1, so it is 10. And next one, next cross multiplication here, so 7 5 here, so minus 7 minus 5 minus 7 into 5 45 45 35 minus 10 minus 45, so minus 45 divided by minus 7, and here we'll get it as 0. And final one is here 45 by 7 you will get if you cross multiply these two values here. Now here we need to find number of sign changes. So from here to here no sign change, it is plus. From here to here only sign change is present, so it is one sign change here. And from here, if you take minus 45 by minus 7 means plus value, so here another sign change is 2, and here no sign change here. That means there are two sign changes. That means there are two poles which is lying on the right half of S plane. So the answer here is C. Okay. Next question. So the next question is phase lead compensation is used to. So phase lead compensation, so it improves the transient stability of the system. So when it improves the transient stability, automatically it will improve the speed of response. So as the speed of the response increases, automatically time decreases. So as the speed of the response increases, time decreases. So automatically as the time decreases, rise time also decreases. As there is a rise time decreases here, automatically the maximum peak overshoot increases. So here the maximum peak overshoot increases, rise time decreases. So D is the right option for this question. Next question. Next question. The output of a linear time invariant control system is C of t for a certain input R of t. So if we are giving R of t as an input to a certain linear system, let me take linear time invariant system, the output what you are getting is output what you are getting C of t. So C of t you are getting here. If you take the same system, and what we are doing is, if R of t is modified R of t is modified by passing through a block whose transfer function is e power minus s. So here it is the transfer function e power minus s we are giving here. So this is the input. Now then the applied to the system, the modified output will be, so input is here, it is R of t, and this is given e power minus t, and this is the output here. Now the modified output is, so e power minus as will makes the system delay, so delay by 1 second. Suppose if we have e power minus 2s means delayed by 2 seconds of time. So output will be c of t minus 1 into u of t minus 1 is a system output. So C is the right answer. Next question. For a feedback control system of type 2, the steady error for ramp input is, so it's a straightforward question. So we'll take type 0, type here 0, 1, 2, and here input steady state error. So ES, so we'll take ESS here. Now it is, first we'll take step signal, second one is ramp, and third one is parabola signal. The steady state error for type 1 system is 1 0, type 0 system is 1 by 1 plus k p, and others are 0, and second one is, so infinity here, and next one is, it is 0, so 1 by 1 plus kv, 1 by kv, and this one is infinity, and for the type 2 system 0, 0, 1 by k a. Okay, so for the feedback control system type 2 system, the ramp is input is 0, so answer is C here. So thank you friends, thanks for watching my video.